Okay, so which means you're supposed to think about it geometrically, and today's geometric condition of interest is the complete intersection property. So I'll remind you what that is. All my rings are going to be commutative and invariant rings, and I'm going to be talking about homomorphisms of such. And this is called locally complete intersection. It's locally complete intersection on the spectral bar, so all P is by R. Let's say this corresponding map should be a complete intersection map, which means really that this definition is simpler if I assume everything is essentially a finite type, which I may as well because it doesn't really make too much difference. Which means if the map is not surjective, I can just throw on some variables to make it surjective. Okay, and then I want this map to be a surjective map whose kernel is generated by a regular universe. So where this is a regular.
The same n, no?
Let's say one of these is an n sequence.
Break it! Yeah, break it.
Which rock is safe?
You might just double the frequency, you know. If it's right.
Okay. That means F1 is a non-zero divisor, F2 is a non-zero divisor modulo F1, and so on. In practice, what this means, for example, if S is a regular ring, which is the main case of interest probably, then it just means that the dimension drops by 1 every time I factor by one of these. So it's kind of geometrically makes sense that I'm intersecting with this property. And it doesn't have to think geometrically. Everything I'm going to talk about is local, so if you want, you can talk about schemes that are just like this map corresponds to some regular immersion, and then this map would be some smooth map. So this is what it means to have a locally complete intersection. Okay, so I'm going to talk about a sequence of invariants that you can associate to any map of commutative rings. And the first one is probably the most famous one. It's just that for this I want to assume S is just a field, so I'm going to take R to just be a ring like this. And then I'm going to talk about the module of differentials, or the cotangent module. One of R over K, which you can define it by just giving a presentation for it. So it's a free module on some generators corresponding to these variables, modulo some relations corresponding to the S, where the df is a different letter. dfj is the sum over I of del fj by del xi dxi. What this really means is that it's the cokernel of this matrix, dfj by dxi. This is the Jacobian matrix of these polynomials. Okay, and this is, geometrically it represents the cotangent shape of this thing, and it also represents the derivations if you prefer to think algebraically, and it's what is invariant. Maybe my favorite example of such a thing is if you take this one here, the field of characteristic zero quality. So take polynomial ring in some number of variables, and then factor by all the symmetric polynomials of positive degree. So all symmetric polynomials except one. In this case, you can take f to be That's a symmetric polynomial, and F2 you can take to be the sum of the squares. And if you go up to degree n, that's enough to generate all the symmetric polynomials. And in this case, if you work out what the...
You probably want an n there in the last.
Maybe it was correct before n done. In this case, if you work out what the Jacobian matrix of this is, up to some constants, is this matrix. One's down here. It's the Vandermonde matrix. So the modular of differentials in this case is the Koszul of the Vandermonde matrix, which is a very special matrix with lots of nice properties, and it means that this is a very special module with lots of nice properties. So, as far as if you're just interested in geometry, the reason why you, or the most classical reason you might be interested in this invariant is that there's a classical theorem called the Jacobian Criterion, which says that if this thing is free, or I haven't said local, so I should say projective instead, of the correct dimension, so projective modulo of rank equal to whatever the dimension of R is, then R is a smooth algebra. R is a smooth okay, so this is kind of the prototypical result of some algebraic condition on a module giving you a geometric condition on a map. There's more. Okay, so the next one I'll write is jumping forwards. Here's the theorem of Ferrand and Vasconcelos independently in the 60s. Which is weakening this condition to weaken this condition correspondingly, which says that in this case, if the projective dimension of the module of differentials is less than or equal to 1, that's equivalent to saying that R is a reduced locally convenient section.
Is the first one if and only F2?
Yeah, this is.
I think that rank condition is more subtle. Think of
Yeah, I'm kind of cheating here, so it's, unless you're local, the rank is kind of like a rank function really, and I'm being sneaky and saying, the right way to interpret this is that the rank function is equal to the dimension function. That has the same rank as the dimension of RP at each parameter. Maybe. But there's no such caveats in here. This just works. There's something funny going on with projective dimension 0, which is will show up at various points in the talk. But this thing has no such worries. This is really only a positive characteristic issue, by the way. If you're in characteristic 0, this thing is automatic. Then you just need to assume it's free. Okay, so you can kind of think of this as a sort of higher Jacobian criterion. At least you slightly weaken this condition on projectivity and you get a slightly weaker geometric condition here. And so the question would be, what happens if you weaken it further? So you say maybe that the projective dimension, this is an R module by the way, I should specify. If this is a module of projective dimension less than or equal to, say, some I, does that give you some correspondingly weaker type of singularities that this ring can have? And well, the answer is supposed to be no. Vasconcelos also at the same time as proving this made this conjecture, Vasconcelos, that in this case, if the projective dimension of the module of differentials is any finite number at all, that should imply that R is convenient section or reduced. Locally convenient section. It's a funny kind of result if you think about it. It's, you should interpret it in rigidity kind of terms, because what it's saying is that as soon as this number here is finite, you have a convenient section, which actually means that it is 1 or 0. So it's saying that a lot of things just cannot happen. There's a bunch of missing behavior, which is sort of typical for this situation. There's smooth things, there's convenient section things, and then there's nothing until you get to very singular things at infinity. And Vasconcelos did offer, he had reasons for conjecturing this, he had very special cases, but I'll write down one theorem, jumping ahead a few decades to Avramov and Koszul in 94, that says if k is characteristic 0, oh, this probably I should put characteristic 0 here. This is false unless you impose something on k or r being like generically separable or something like that, but characteristic 0 is definitely fine. So if k is characteristic 0 and r is a graded ring, so you assign your variable some degrees, some positive degrees, and the f's have to be homogeneous polynomials, then the conjecture is true in that case. Okay. So yeah.
Graded means n-graded.
N-graded, yeah.
Traded in, or is a positive degree or something.
Yeah. So yeah. Connected graded. Connected grading. Okay. This philosophy of like higher Jacobian criterion is due to these guys. This the title of this paper is Higher Jacobian Criteria for various things. Not the title, but there's the word Higher Jacobian Criterion there. And this is how they're thinking of this result as some kind of higher Jacobian criterion.
Can you explain what you mean by graded? I mean, I know what graded means, but how is it a hypothesis here?
No.
Why can't you put all in degree 0? And you mean with the
Yeah, sorry.
grade?
Standard grading.
Not necessarily standard graded, but it's connected graded with respect to some grading if your variables have a strictly positive degree. Yeah. Okay. Okay, so here's another invariant, the conormal module. So this invariant works best if you assume that this map is surjective. And then it has some kernel I. And R is just a quotient of Y like that. If it's not surjective, that's actually not really an issue. You just do this trick of adding some variables to make it surjective. And then you look at the kernel of that map instead. And in this situation, the kernel module is module I mod I squared. So the ideal I is manifestly an S module, and if you do this construction to it, it becomes an R module. Because if you multiply anything in I by something in I, it goes into here. So this is the one R module. And it is geometrically, maybe the name is sort of suggestive. It's saying that one thing you can do with it is dualize it, get a normal module of R over S, which is just like this, and it looks sort of like if this was spec S and spec R is some closed subset of it, then this normal module corresponds to the bundle of normal directions that R can move on. The directions that you can move spec R inside spec S. So it's kind of this module here is telling you about the definition of theory of this inside here. I think. So it makes sense that if this is a particularly nice kind of bundle or sheaf, then maybe the singularities of this map are particularly nice in some sense, and that is indeed true. So this could be better. Is it too early to sing?
I did get the board dry though.
Oh, yeah, it worked pretty good.
Straight off.
So here's a corresponding Jacobian type theorem for the conormal module. This says, again, independently due to Ferrand and Vasconcelos. It just says that, so here we want to assume that that I is an ideal of finite projective dimension. This is some kind of background regularity assumption. If you assume that S is a regular ring, which is kind of the main thing to have geometrically in your head, then this is vacuous, is automatic. In that case, this module is projective. Even only if I is locally generated by a regular sequence, so or S2R is a locally complete intersection map. Okay. So same thing holds in that case. Projective here just means that this, well, not that one, but the dual one, this is a vector bundle. Right? So it's deformation theory inside because it's kind of as nice as possible. You can just freely deform it, at least infinitesimally or something. So it makes sense that that would be the nicest case. And then correspondingly, there is a conjecture. I would once again maybe hope that you can weaken this condition and get weaker geometric conditions here, but it turns out that's not really the case, at least not according to the evidence that Vasconcelos had. So the conjecture was that at least if you weaken it just according to the projective dimension, so again, dimension over S is finite, then
Dimension of what?
so you have some ideal finite projective dimension inside some commutative Ethereum ring. Then if the projective dimension of the conormal module is finite, then I is generated by a regular sequence. So same as this, the map from S to R is locally completely definite. Okay. Again, so there's various, what shall I write down? So Vasconcelos himself had various amounts of evidence for conjecturing this at the time in 1978. There was already some evidence around in the literature that in 1969 had proven that it's true when the projection dimension of I mod I squared is less than or equal to 1. So it's not one of those funny theorems if you look at it. What it's really saying is that if the projected dimension is less than or equal to 1, then I is generated locally by a regular sequence, and so it's actually projective, and so it's 0. So it's saying that 1 cannot happen. 1 is impossible.
Do you have a characteristic restriction here?
Not on this one. So this again is this this case of the modulo of differentials, there's annoying separability type things happening all the time, and it makes that case generally harder. All of that goes away when you look at the conormal module. There's no issue about that. Okay, there are various other things going towards this. Maybe I was trying to Avramov and Hausdorff in 1994 proved this is again true if S is a graded ring. This time there is an assumption on the characteristic, but turns out not to be an intrinsic thing about the thing. It's just the proof does use characteristic 0 in this case, and R again should be graded in this case with positively graded variables like that. Okay. So they settled this case, and then it turns out to be it is true in general. There's a paper from last year that says conjecture is true in general. And I'll talk a little bit about proof of this later, but I want to move on to one more module before I
It's worth pointing out that this implies that this conjecture implies Taylor differentials conjecture.
Wait, by doing the diagonal thing?
Just for less than or equal to.
Implies the differential? Really?
With minor hypothesis, right? We'll talk about it later.
I mean, we know this one and we don't know that one.
We'll talk later.
Okay.
I know what you mean.
There's this enveloping algebra trick, it doesn't. There's. Okay.
Oh, maybe I was mistaken. Yeah.
I think I know what you mean. I don't think that you could do that.
You could have took two conjectures, you know.
Yeah, so far two conjectures. One of them is known and one of them is actually still open in general. The first one is still open, but it's known for graded rings of characteristic 0. Okay, one more module.
So who's this theorem due to?
Dash. Dash B. Okay. One more module. Okay, so here's another invariant that you can associate to any ideal. So let's say I, again, is an ideal in some commutative ring. And you can say, pick some generators for it, so F1 to Fn like that. And you can define the first Koszul homology module of this ideal. Usually the reason why this H1 of I with coefficients in S. If you know about Koszul complexes, this is just the first homology module of the Koszul complex over S on these polynomials. If you don't know about that, then there's kind of a simple way to think about this. It's just you take all the relations in the ideal, the relations between the relations, otherwise known as Syzygies, which means take those elements F1 up to Sn in S to the n, such that the sum of Si times Fi is equal to 0. So any kind of combinations of the polynomials which yield 0, those are relations between the relations. And then you factor out by the trivial relations, which is that if you think about it, if I go to the jth place and put Fi, and if I go to the ith place and put Fj, I get the same thing. So I put a minus sign here, and then 0 everywhere else. That just gives me Fi times Fj minus Fj times Fi, so that's always going to be 0. So these are the trivial relations. And if I factor out by all of those, that's exactly what the Koszul homology is. It's just relations that exist between my relations modulo the trivial ones. And it kind of makes sense that this is a useful invariant because it tells you how trivial the relations are between your polynomials. And it's exactly the same thing as the first Koszul homology. Know about that. Okay. And I want to convince you that this actually fits into the same picture as these other two modules. It's the geometric interpretation is getting a bit looser. It's maybe some Jervy thing or something, but it is still something that you can try to do Jacobian criteria to. And maybe I just pressed too hard. That's probably what's going on. There's a theorem in this case of Gullickson from the 60s, 1969, that says if, so again you want to assume this is an ideal of finite projective dimension over S. So assume this has finite projective dimension over S. So again, if you take S to be a regular ring or just a polynomial ring, then that's irrelevant. It's automatic. What's more interesting is the condition that you put on this Koszul homology module. If this is a projective module, over this portion, it's not really 100% obvious from this presentation that this is actually an R module, or a module over S mod I, but it is. And if it is a projective module over this, then it's actually equivalent. I should probably, okay, well, I'm doing slightly out of order, but it's okay. Then our I is minor by locally taken by regular sequence, so S to R is locally conjecture. What the Koszul homology, so the Koszul homology is classically used to do this, to detect regular sequences, and this is kind of a weird version of that. So I should probably start people who are taking that so that we can sneak this in here. It's a kind of classical fact. I don't even know who to attribute this to. It might be just Jean-Louis Koszul or Elia, probably.
From the book's form.
Sorry?
From the book's form.
From the book, okay. Okay, I'll trust you. From the book, this fact that if this module is 0, it kind of makes sense that this is equivalent to having a regular sequence, or at least locally having a regular sequence. So the first Koszul homology is 0. That's actually equivalent to the whole Koszul complex being acyclic in all positive degrees. So the Koszul complex is then a projective resolution of your quotient. And that is equivalent to S to the quotient being locally contained section, i.e. the ideal is locally generated by a regular sequence. Yeah. So, and that's an extraordinarily useful characterization of regular sequences. It's like, depending on what sort of mathematics you do, it's, if you're working with convenient section maps, you're probably using this sort of thing constantly. And there's this funny generalization of it, that you really only need this thing to be projective. And again, it's this weird rigidity type thing that as soon as it is projective, it's actually 0. So it can't really even have projective dimension 0 in this case. Like as soon as it's projective, it disappears. You can probably guess the next conjecture. Well, actually no. Maybe this was a question. It was around, and it turns out there's a corresponding theorem. From last year that says that as soon as this thing has finite projective dimension, the same thing happens. So, any ideal of finite projective dimension, if the projective dimension of the Koszul homology as an R module is finite, then S to R is locally contained. So there's some unusual rigidity thing happening to all of these modules, that there's somehow smooth things and convenient section things, and then all of these modules fail to detect any other kind of singularities, at least in terms of their projective dimension. There's just a missing behavior.
you probably said this, but this also implies that all higher homology vanishes.
Yes, so in this case, as soon as it's exact in degree 1, it's everywhere.
What if I use like one of the relations of y?
Yeah, well, I was going to say there's a trivial.
Then it's projected.
The whole thing is, I see.
It's a local criteria, really, because the distance between the Koszul homology vanishing doesn't tell you it's a regular sequence unless it's in the local case. When you have these Koszul regular sequences that are not regular,
Yeah, but I thought that that's not.
you have to be a bit careful. And Paul said if you take two copies of the same relation, you can't do it.
You add an fn plus 1 which is in I, and then you just get a copy of R mod I.
I mean, just take a 0, right?
Okay, so this, yeah, okay. So this
For example, was
okay, so for this one you want to assume it's a local map. This version I think actually fixes that. Because projective summands can show up if you present your ideal in a non-minimal way.
Correct.
So that one is suspicious, but this one I think is okay. Yeah, if you add on extra relations that you don't need, you just get projective summands, which means so fix it like this. Okay. Oh, and that reminds me, the result that Galaxian also proved was in fact stronger, that as soon as there is a at least, okay, that's in the local case. If this is a local map, then as soon as there is a non-zero projective summand here, it's a convenient sector map. And the corresponding result here is unknown, whether maybe you have some undefined projective dimension or something like that, whether that's enough. Okay, so three different classical invariants you associate to a map here, and three different kind of rigidity results associated to them. And now I want to talk about the cotangent complex, which is another important invariant, and how it actually kind of ties all these three things together. The cotangent complex. Let's just use Quillen's definition, which is we're thinking about the modular differentials. So we have, say, from commutative S algebras, we can get S modules, and this is going to take a commutative S algebra R and just send it to the modular differentials. This is actually an R module, right? But since R is changing, it would be just awkward to set up that category, so I'll just write this, that's fine. Quillen invented derived functors and then defined the cotangent complex to be the total left to right functor of this thing. So, at least for him, and then embedding this into superficial commutative algebras, and over here talking about S chain complexes, and taking the total left to right functor here, defining it to be, defining the cotangent complex to be the right functor of this thing, which is R maps to this cotangent complex. The right functor of omega S at R. Okay, so this is our cotangent complex. I'll just say maybe here's a sort of very quick example of what this means in practice. If we take S to be a field, and we take R to be this truncated polynomial like this, then there is a simplicial resolution. That looks like, let's call it A. It is freely generated by two non-degenerate simplices. X is the same X as before, and Y is some degree 1 simplex, which means you just have to specify with sort of two n's. And you can specify it like this. So in a picture, it's sort of, here's Y, and what it does is it kills this cycle x to the n by connecting it to 0, like that. So this is a simplicial algebra, and it is in fact a resolution of this commutative ring here. And so the cotangent complex in this case is just, it comes from taking the differentials of x and y. So it just gives, in this case, we get a dx in degree 0 and a dy in degree 1, and it's the free R module of those two things, and it has a differential which takes dy to x to the n times x to the n minus 1 dx. So it just differentiates like that. So whether or not, I guess the cohomology, or the homology of this complex depends on whether n is 0 or not in K. And it depends on the characteristic.
In that case, you could say that L is the Koszul complex for the Jacobian, right?
L is the Koszul complex for the Jacobian.
In this specific example.
Oh yeah, in this specific example. Usually there's usually the Koszul complex is a lot bigger. It's an algebra. The beginning of the cotangent complex is always just Jacobian matrix, right? And if you have a complete section map, then it is just the Jacobian matrix in degree 0 and 1, and then nothing else. Yeah. And usually there's a lot more to it. When Quillen introduced the Koszul complex, immediately after introducing it, somehow he just knew all about it and made the conjecture that if the cotangent complex is perfect, again, this should be for S2R being a map of finite flat dimension. So most of the theorems have this kind of hypothesis at the beginning about like having an ideal of finite projective dimension or something, and it's kind of necessary for everything, and it's some regularity assumption, and there are still open questions about what goes on when you drop these things, but they're quite difficult. But there's all the way. In that case, if you have a perfect cotangent complex, which means it is equivalent to a bounded complex of finitely generated projective modules, then S2R is a locally convenient section map.
So this is perfect over S, right?
Thank you. Yeah, so despite, I mean, you can set this up more carefully so that you know you're going to get an R module at the end, but you do get an R module or a complex of R modules at the end. So this is a complex, a connected complex. So we can either L0, L1 of R modules defined as homology. So the usual story, if you take a different simplicial resolution, we get a this is a theorem of Avramov, which is a theorem of Avramov and Heron in the 80s in characteristic 0. And Avramov in 1000 in general, which says that yes, the conjecture is true. If your cotangent complex is bounded, then it is a locally convenient section map, and in fact, it has to be concentrated entirely in degrees 0 and 1 like this. There's nothing beyond that. Okay. L is just sort of L0, L1, and then nothing else. Okay. Yeah. Okay, so just find. So in this paper, Higher Jacobian Criterion of Avramov and Hausdorff, which I mentioned, they introduced another sort of a construction that you can do the Koszul complex to produce interesting invariants from it, which is we're trying to get to the title of the talk, the Syzygies of the cotangent complex. So the Ith syzygy, or the Ith cotangent module, they call it, of the cotangent complex is the module omega I L of R over S. It's just going to be the cokernel of the Ith differential in there. So the cokernel at degree I. So I just wanted that. This is where. So to make this well defined, I told you this is only defined up to homotopy. You need to make sure that your cotangent complex is represented at least by a complex of projectives. So this is where L has a complex of projectives, bounded below complex of projectives. Proposition says this is well defined up to projective summations. So if you take a different projective resolution of your cotangent complex, you will at least get the same answer up to possibly direct sums with projective modules. And since I'm interested in questions like the projective dimension of these things, that doesn't matter too much. And it also means that you know about these things, it's going to be well defined as an object in the singularity category, which tends to be a nice way to think about things. And in fact, if this whole time, which I think I told you at the beginning, you're allowed to think geometrically the whole time, with this x instead of this r. This is one case where if you are thinking in terms of schemes, then it's not well defined up to projective summands because you have this issue of like these things don't split globally, they sort of split locally off. And that means the correct way to do that is to think in terms of the singularity category, where these two, this is a well defined object of the singularity category. Anyway, and the proposition as well, and moreover, in degree 0, this one is kind of predictable. What happens in degree 0 is just a co-kernel of the zeroth differential, it's the same as the zeroth homology, and kind of by definition of your taking a direct functor, you get back your multiple differentials. Like this. Oops. In degree 1, this first syzygy of the cotangent complex, that's this conormal module, I mod I squared, where I think I mentioned this before, if this is not a surjective map, you just do this trick of adding variables to make it surjective, and then this ideal is the kernel of that map. And so in this case, in degree 2, this is the Koszul homology. And then so on. You have generalizing each of these three modules that we saw. There's an infinite sequence of kind of modules that are showing up. And you can ask for Jacobian type criteria for all of them. And there are Jacobian criteria for all of these. I'll write down in a minute. Avramov and Hausdorff. They proved, again in this characteristic 0, and actually S being a field in this case, and R being graded, so connected graded with respect to some, generated by some variables in strictly positive degrees. In this context, they proved that if for any I at all greater than 0,
do you mean S equals K?
yeah. So
These maps are going from S to R.
yeah, so we're talking about upper maps. Yeah. So in this case, it's like an absolute thing. We're talking about the cotangent complex of just R over a field. You have to interpret these as about choosing some factorization like that, and setting I to be the kernel pair.
Thank you.
Okay, in this context, they proved that if there is even a single I greater than or equal to 0, such that the projective dimension of one of these Syzygies is finite, then R is a locally convenient section. In fact, a convenient section ring, because there's no local if you're graded, everything is local finite. The main result was Sri. So this would be Iyengar from here. Is that with no such assumptions here, so this would just be, well, one such assumption here, but this general thing which is definitely necessary. R2S is some map of finite part dimension. With no assumptions on the characteristic or being graded or anything like that. And it says that if there is a single I greater than or equal to 1, such that the projected dimension of one of these cotangent modules is finite, then this map is locally convenient section.
So in the LCI case, does it work out that all the omega i's are projective? Is that?
Yes, so and then you can say, in which case L is just, this cotangent complex is just, I guess there's a Jacobian map, and then there's this, and then there's nothing else. That's what the cotangent complex looks like for a convenient section map. And it's saying that, so all these omega i's are projective. And it says that here the omega 0, 1 has projective dimension less than or equal to 1. So there's this sort of shifting thing happening at the beginning, but other than that, they're all projective. There's this weird caveat going on here. So the result for I equals 0 is false in general. There are just like all sorts of positive characteristic counterexamples. But with some assumption added on, like characteristic 0 or some separability, it should still be true. It's just that don't know how to prove it. It's known to follow from another conjecture of Eisenbud and Mesa. So it's still expected to be true, but don't really have any methods for it, except for these methods, which are definitely only for graded things. Like that. And maybe I'll just make a remark.
Isn't that result actually from next year?
I think this one is I think it's a PID now. I don't know, or I guess in print. I don't know what the difference is. There's Street Tree shaking his head, which I don't know. It's appeared. Okay, it's official.
But in the 2023 volume.
Okay. It will physically appear next year, but it is digitally. Okay. Yeah, so we're planning on proving this. Okay, so just a remark is that this is like it's a proof of Quillen's conjecture. is if this is perfect, then it's a bounded complex of finally generated projectors, and then you do the Syzygies construction. Past a certain point, there's nothing, and you just get zeros. That implies that these are 0 for all large enough I. You only needed a single one to have finite projector dimension, but you've got them all 0 eventually, which is pretty good. So that implies that you have a commutative section map, and it gives you this conjecture up here. And I think I mentioned here that the positive characteristic case is kind of significantly harder than the characteristic 0 case, but somehow this proof here has nothing to do with the characteristic. It just works the same in all characteristics. It's nice. I'll just say a short thing about the proof.
It's worth saying that actually what the result shows is that you just need one hole in the cotangent complex.
Yeah, so it's not just so this conjecture is about the cotangent complex ever just stops completely and then it's 0 forever. Then you have a commutative section, but you only need if it splits up at all and having a gap, and these Syzygies detect that gap, and so you can tell that you have a commutative section. So it's saying that the cotangent complex is very, very non-trivial. It never has any kind of gaps or anything. It just gets more and more complicated. So this, where's it gone? This result of Avramov and Hausdorff is also stronger in that case. In the graded characteristic 0 setting, you can prove more. You can prove that the cotangent complex is actually growing exponentially. And each of these Syzygies modules has a minimal projective resolution, which is growing exponentially. And those sort of statements, we don't know how to prove those in general. We only know how to talk about that projective dimension being finite.
Is there then an interpretation of the growth rate?
Yeah, well, the word for it is complexity. And there are all sorts of nice. So if you have this is a characterization of convenient section rings. I guess the moral of the story is that there's lots of characterizations of convenient section rings that look like this, and it's philosophically something to do with this elliptic hyperbolic dichotomy, if people have heard of this. One such characterization is that a ring is convenient section if and only if, let's say it's a local ring, because then you can talk about minimal resolutions. A local ring is convenient section if and only if every module has a projective resolution which is growing polynomially, and the rate of that growth is called the complexity. And there is a nice interpretation of that. It's that if to every module you can associate a variety, and that complexity is the dimension of the corresponding variety. There's generalizations of that picture that Josh has worked on, and I've worked on about associating varieties, any module over any ring, but it's a bit more complicated. Okay, so just finish up by saying, the proof. Uses this Atia character, which briefly showed up in Janina's talk yesterday, which is that, so one thing you can do whenever you have a ring homomorphism is look at this kind of diagonal map, like this. You take it to enveloping algebra, and then look at the multiplication map of the ring, and you can look at the kernel of that, or at least in the drive sense. So you take a triangle, this form. I think the title of this conference is triangles and something, so there's one triangle. And then Quillen proved so what I'm going to write technically makes no sense, but if you take this to be a simplicial resolution to compute this direct tensor product, then it doesn't make sense. You can take J1 squared, get a simplicial ideal and a simplicial commutative ring, and this thing is the cotangent complex. And so in particular, you can look at the corresponding connecting map there, and you get a map from R to the shift of the cotangent complex. by looking at the map from R to J and then projecting down onto this and saying that that's the cotangent complex. And this is called the universal Atiyah class of this map from ROS. This name is due to, I think, booklet and planner. So we can call it the Atiyah map. The name comes from these Atiyah classes which show up. If you tensor this with a module, you get a map n to the suspension of n tensor L, which is, you can think of it as a class in x1 m from here to n degree 0, you will just get this. x1, if m is a module, you just get this. And these classes in X were defined by Atiyah and used as abstractions for connections on vector modules and stuff like that. Well, this is kind of a global thing. These aren't very interesting in the local case or in the affine case, but the name comes from someone like Atiyah. But we're going to use these. We use these this Atiyah map in a kind of a different way. I'll just say what it is. And by the way, so here's an important caveat: is that this is all happening in the derived category of descendality algebra, which is to say it's sort of the derived category of bimodules, and this map here is a map in the derived category of bimodules. Even though both of these sides here are complexes of R modules, this is not a map of complexes of R modules. It has to be defined in this larger derived category. I'll just say. Just by composing with the Atiyah class, you get this map X to R L. Let's put this in there. And because of the shift, it has degree +1, and this thing here is known as Quillen homology. X out of the cotangent complex, that's how one defines Quillen homology, and X computed over the enveloping algebra, that's how one defines Hausdorff homology.
So over on the left-hand side here, this should be the enveloping algebra for the class itself. On the bottom left there.
Yeah.
This X, is that supposed to be over R, or is that supposed to be over?
That is over R. If you think about it, if you take the Atiyah class and tensor it on one side, so it's a map.
Oh, so you're going to eat up one of the
you use one
R's.
side and you tensor and you have one side left.
Yeah. Okay.
I think I'm already over time, so I will say the theorem is about trying to understand this side, about like when this is, say, bounded or something. If this is a perfect complex, and this would be bounded. This side here is much easier to understand. Hausdorff homology is easier to compute and easier to prove theorems about than Quillen homology. And so the proof just goes by showing that this map here, involving the Atiyah class, has certain equivariance properties, and then formally deducing everything you would like to know, not everything, lots of things you would like to know about this side just from known maps about this